Welcome to the deep dive.
Hello.
Today, we're getting into some sources about a real cornerstone of geometry, the Pythagoras Theorem.
Absolutely. We've got material looking at, where it came from, different proofs, and how it's actually used.
Right. And our mission, as always, is to really distill the key takeaways for you, get you the core insights fast.
Okay, so where do we begin? History seems like a good place.
Yeah, the origin. You hear Pythagoras, you think ancient Greece, obviously.
But what's really fascinating in these sources is this mention of Budayan, an Indian mathematician.
Oh, right. I saw that developing something similar, like way earlier.
Yeah, around 600 BC, centuries before Pythagoras, though Pythagoras gets the credit for the version we mostly use.
The standard, equation form.
Exactly. And that core idea itself is, well, it's pretty elegant. It's all about right-angled triangles.
Triangles with that perfect 90-degree corner.
Uh-huh. And for any triangle like that, there's this fixed relationship between the side lengths.
Okay, so you have the two sides forming the right angle, and then the one opposite, the hypotenuse.
That's the one, the longest side. And the theorem just says the square of that length equals the sum of the squares of the other two sides.
AC squared equals AB squared plus BC squared. That old chestnut.
Right. Or think of it visually, like the sources suggest. Imagine drawing actual squares attached to each side of the triangle.
Okay.
The area of the big square, the one on the hypotenuse, is exactly the same as the areas of the two smaller squares on the other two sides added together.
Ah, so it's really an area relationship that tells us about the lengths. That's neat.
It is. And the sources touch on how we know it's always true. It's not just stated.
Right, the proofs. They mentioned a few ways.
Yeah, like using those areas we just talked about, rearranging shapes to show it visually, or using ideas about similar triangles, different angles proving the same thing.
That consistency across proofs really cements it, doesn't it?
Totally. And that leads to something else important in the material, the converse.
Meaning it works the other way around.
Exactly. If you just pick up any triangle, measure the sides, and find that, hey, the square of the longest side does equal the sum of the squares of the other two.
Then it has to be a right-angled triangle.
It absolutely must be. No question. It's a test.
Which is, well, super useful. The sources give that classic example, the 3, 4, 5 triangle.
It's a Pythagorean triplet, yeah.
Because 3 squared is 9, 4 squared is 16, add them up, you get 25.
And 5 squared is 25. Boom.
So any triangle with sides 3, 4, 5, whatever the units are, feet, meters, inches, it's got a right angle. Guaranteed.
And you see how this jumps right into, practical problems. The sources have that ladder example.
Oh, yeah, the street crossing one. Okay, so a 17-meter ladder.
Uh-huh. Leaning against one side of the street, it reaches a window 15 meters high.
Okay.
Then, keeping the foot of the ladder in the exact same spot, you swing it across to the other side of the street, and it reaches a window that's only 8 meters high.
Right, so the ladder length, the hypotenuse, stays 17 meters. The heights change. We need the distances on the ground.
Exactly. So first side. Ladder is 17, height is 15. The theorem tells us the ground distance. It's 107 ton and 2 do minus 100 for 102 $2.
Which is 289 minus 225. That's 64.
Right. And the square root of 64 is 8. So 8 meters from the wall on that side.
Okay, got it. Now the other side. Ladder still 17. Height is now 8.
So 107 minus $82. That's 289 minus 64.
Which is 225.
And the square root of 225 is 15. So 15 meters from the wall on that side.
So the total width of the street is just 8 meters plus 15 meters.
Which is 23 meters, found just by using this one theorem twice.
Pretty clever.
And the sources kind of hint that this isn't just the end of the story,
How so?
Well, this theorem, it's fundamental for understanding relationships in other kinds of triangles, too, like acute or obtuse ones. And it's a stepping stone for geometry in 3D and, well, higher dimensions even.
So it really opens doors.
Definitely a foundational piece.
Okay, so wrapping up, we have this core idea, maybe even older than Pythagoras himself.
This elegant link between the sides of a right triangle. The square on the hypotenuse equals the sum of the squares on the other two.
An area relationship, really.
Yep. And it's not just definition, it's a tool for measuring, for proving things. Super practical.
It really makes you pause, though.
Yeah.
How can one sort of simple, ancient geometric rule end up being so critical for, well, everything from building houses to understanding physics and space itself? It kind of leaves you wondering, what other simple relationships might be out there just hiding that hold that kind of incredible wide-ranging power?